Hello everyone, my name is Semsu Bakan, and I'm going to be talking to you about our speech separation work using transformers today, and I hope to see you in the conference as well. So welcome, thanks for stopping by. I will be talking to you about our work on speech separation using self-attention, as I mentioned in the introduction. This is a joint work with Mirko Ravanelli, Samuele Cornell, Mirko Bronzi, and Jian Yuanzong. And I would like to mention that this work has been part of the Speech Brain project. Within our repository, all of our code and in fact also the pre-trained models are available. I invite you to check out our repository. All right, with that, let's begin. So let me start by talking about the problem that we attack in this paper. So we basically work on single microphone source separation problem. And with that, what I mean is basically we are given a mixture signal in which K sources are hidden. In the figure, we have two sources. But we aim to build a separation model which can recover these original sources as close as possible to their true values, right? And this has application in music production, hearing devices, EEG signal separation, even like a pre-processing step in automatic speech recognition, and many more, right? And we propose Sepformer, a self-attention-based source separation architecture that we are quite excited about, which obtains state-of-the-art results, right? So with that, let's move on. So what is self-attention? So self-attention is essentially a fully feed-forward architecture which enables us to model long sequences, or more correctly, sequences with. It enables us to model long-term dependencies in sequences. Okay, better put. And it is the basis of the transformer architecture, which obtains state-of-the-art results in domains such as natural language processing, computer vision, speech recognition, just to name a few. And by kind of leveraging the power of self-attention, we are able to obtain state-of-the-art results on, I will show you several different data sets, but on this, for example, on the standard benchmarking dataset of WSJ02 mix, we are able to obtain state-of-the-art results as of April 20, 2021. So now the question is, how can we apply self-attention on source separation? So to the best of our knowledge, a fully self-attention based model did not exist in the literature until our paper. Basically, it is not straightforward to apply self-attention directly on, let's say, spectra or something like that, because self-attention has a quadratic complexity with respect to length of the input sequences. All right, so we have to find like an efficient way to model real-world signals. All right, so for this we employ the dual path pipeline that is proposed in the paper by Luo, 2018, the dual path RNN paper. Right, so basically what is done is we chop the sequences into chunks, and a so-called intra-model models the dependencies within chunks, and an inter-model kind of models the dependencies across chunks, and kind of a combination of the two is used. And so if we want to kind of see what this means if we use a transformer processing block inside the dual path pipeline, what this amounts to is the intra-block essentially calculates a block diagonal attention map, and the inter-transformer that we call applies like this strided attention structure. And overall, we use 50% over between the chunks. So, okay, with that, let me kind of define what our model is, what our complete system is. So we use the masking architecture, masking-based architecture that is like fully learnable. It has fully learnable encoder and decoder blocks, which are essentially convolutional layers. And we basically learn a deep masking network based on self-attention, all right, which estimates element-wise masks. And once using those masks, we do the separation in that representation space. The decoder reconstructs the signals in the time domain. And the structure of the masking network is as follows. The representation H that is shown above in the overall pipeline is first goes through a linear layer, and then we apply chunking. That is basically the operation that I showed in the previous slide. And afterwards we apply Sepformer, which is essentially which combines sort of like short-term modeling with long-term modeling, right? Which is based on the dual path pipeline. And once that processing is done, we go through a linear layer, and afterwards there's an overlap add block, which kind of undoes the chunking operation. And afterwards we finish up with feed-forward layer and a ReLU. And afterwards we get our separation masks. All right. And the Sepformer block that we show on the first row of the masking net, on the second row, I guess, as I've showed in the previous slide, combines the intra-transformer block, which models the short-term dependencies, with the inter-transformer block, which models longer-term dependencies. And for the transformer block, we use a pretty standard architecture. And we train this model in a supervised with supervised training using the permutation invariant SISNR loss. Right. So as to describe the dataset, we use the WSJ023 mixed dataset, which consists of mixtures of 2 and 3 speakers respectively, and the relative gains are randomly sampled between 0 and 5 dB. Right. And in this dataset, there's 30 hours of speech for training, 10 hours for validation, and 5 hours for test. All right, so with that, let me start talking about the results we get. So on WSJ02 mixed data set, when we apply dynamic mixing, that is, if we create new mixtures on the fly, basically we see that we are able to obtain state-of-the-art performance number. But one thing to note here is that we use a stride factor of 8, and I will show you in the upcoming slides that this enables the model to be less memory demanding, and it makes it faster in terms of inference time. On mixtures of 3 speakers, we kind of widen the performance margin between us and the closest performing model, and so as you can see, there is a significant performance gap. And now let's take a listen to an example separation.
The shares closed at
shares will have 10 votes each, comma, while the existing common shares. The Class B shares will have 10 votes each, comma, while the existing common shares.
The shares closed at $18.25, up 25 cents.
The Monsanto spokesman said, "There is very little we can say."
All right, and with that, let me talk about the speed and memory comparison with other methods. So in terms of average forward pass time, as you can see, here the x-axis is the input sequence length, and the y-axis is on the left plot is the time required for forward pass time. We see that our model is faster in inference time, and in terms of memory usage, we also see the same trend, a similar trend. We see that it's more efficient in terms of memory usage, mainly because we use the model is able to obtain these good results with a large stride factor. And in terms of training speed, if you compare with these two approaches, we see that our model trains faster. All right, so up until this point, I've been talking about the results in the paper, but also like after the paper, after the submission, we extended our results to other datasets. So for instance, on the VAM dataset that introduces environmental noise to WSJ 2-mix dataset, we see that we obtain state-of-the-art results, even if we don't use dynamic mixing. And the version where there is reverberation is present, also we see that we obtain state-of-the-art results. Now let's take a listen to an example separation here.
Second,
For now, however, Japanese manufacturers are managing to adjust to what would have seemed, a couple. For now, however, Japanese manufacturers are managing to adjust to what would have seemed, a couple.
second is Admiral Poindexter believes what he and Colonel Lawrence were doing is legal.
And let me give you an example separation result on a real-life mixture. So I basically asked Mirko, my co-author, and the leader of the SpeechBrain project, to record a real-life mixture on basically captured by a cheap microphone in a reverberant environment, and let's see if you like the results.
See, I left your packet on the desk. Oh, thanks. It's finally here. My secret weapon, double-sided ELIDA tape. Gone are the days of the sticky, messy double ELIDA glue.
See, I left your packet on the desk. Oh, thanks. It's finally here. My secret weapon, double-sided ELIDA tape. Gone are the days of the sticky, messy double ELIDA glue.
Hi everyone, welcome to the recording for our Sepformer that we hope is working very well with the real recording. That's all.
All right. So as you can see, the results are promising, to say the least. We are quite excited to share these results with you. And one other thing that we are quite excited about is the SpeechBrain toolkit. So this project has been part of the SpeechBrain toolkit, which has recently been released. And you can find all of our code and all of the pre-trained models within our repository, and Hugging Face, basically. So as to conclude, we propose the Sepformer, which is a fully attention-based masking architecture for source separation, and it obtains state-of-the-art results in speech separation. Sepformer is less memory demanding and faster than the best performing models, because mainly because we are able to subsample the input 8 times more than the closest performing models, but we still retain the performance. And as I've said, please check out the SpeechBrain project. Our results are very reproducible. The pre-trained models are available on Hugging Face. Thank you for your attention. Hope to see you in the conference, in the poster session. Looking forward to talking to you. Bye now.